Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. This is the last video in our chapter on recursion, and in this video we're going to talk about Quicksort. So Quicksort is another divide and conquer recursive sorting algorithm, and unlike the merge sort, it does all of its work going down the call stack. Also, Quicksort can be implemented in a way where it works in place so that you can sort an array and keep all the values in that single array. However, we're not going to write that particular approach right now. We're going to write something that's a lot easier to write. In a later chapter, we'll come back and we'll approach Quicksort, look at it again, and write a very efficient Quicksort. But for now, I just want to write one that works and that shows you how Quicksort is done. So once again, if we look at an array of values, the way that Quicksort is supposed to work is we pick one element and we make that element special. We call it the pivot. Okay? And so in many ways, the quality of Quicksort depends upon how you pick the pivot and how good the pivot is. The easiest way to pick the pivot is just to say, hey, we're going to make the first element into the pivot. This approach, while it's easy to code, winds up being less than ideal in many ways. In large part because if your array is already sorted, that turns out to be a very bad pivot. But that is the approach that we're going to do for now. A better way to do it is to pick an element randomly from here. Once you've picked the pivot, you break the remaining elements that you have into two subgroups. The elements that come before the pivot and the elements that come after the pivot, and then you stick them all together. And so, for example, here, if we made our 5 into the pivot, I would want to pull out and make one collection that was the 2, the 3, the 1, and the 4, and call Quicksort on those, and then have another one, which is the 7, or the 9, the 7, the 8, and the 6, and call a Quicksort on those, and then take the results of those Quicksort and put the first ones together with the 5, which was our pivot, together with all the ones after it. And so, assuming that the pivot is close to the middle, this breaks things in half. If your pivot is basically a random element, it will, on average, be in the middle. It turns out that you'll wind up with about 2 times log n levels, which is still order log n. And so we want to write some simple code that executes this algorithm. So this is the code that we had for our merge sort previously. I'm going to write a Quicksort, and once again I'm going to do this with lists. Now in a later chapter we will write one that works with arrays, that does it in place, and that is a fast and efficient Quicksort algorithm, but that's not this chapter yet. For this chapter, I want to write something that actually is very easy to write. And in particular, what we're going to write is a Quicksort that uses some of the higher order methods to work through things. So what I want to do is I want to take my pivot and make it equal to the head of the list. And I'll just call it P. Okay. And then I want to take all the other elements that are in the list, which will be lst.tail, and I want to partition them. Now, you can write a more succinct version of this that uses 2 different filters, but instead of you calling filter twice, I'm going to call partition once, and it's actually going to be a little bit more efficient. So we'll get the elements that come before the pivot and the elements that come after the pivot, and they will be equal to lst.tail, because I don't want to include the pivot in this, dot partition. Now remember, what partition does is it's like a filter and a filter not all at once. So the things that I want before are all elements that are less than P, and then the stuff for after will be everything where that's not true. Then the result that I want to return is what we get if we do a Quicksort on the stuff from before and we're going to attach that onto the value of p const onto what we get from the quicksort of the after. And there we go. Let's see how well this works. So instead of doing the merge sort here, I'm going to change this to quicksort and see if that is happy yet, or if I have typos or what I've messed up. So once again, we should start with 10 random values. Whoops. I have an infinite recursion. Oh, never mind. Yes, indeed, I do. I have a recursive function here. We have to have a terminating condition. If t dot length. Actually, I'd rather do this with a match. LST match. One case is nil, in which case we give back nil. If I have a case of an x cons nil, in other words, a single element, I want to give back that list. Case of anything else, we do what we had written before. That will prevent us from having an infinite recursion. And here we go. Okay, so elements originally out of order, elements after sorting in order. We run it again. Once again, elements in order. And again. Okay, so this is our quicksort. You can see the quicksort is actually significantly shorter than merge sort. If you were to play around with it some, you could make this even shorter than what we have here. But this works well, and hopefully is fairly easy to read. Once again, this is working on lists, so it's not happening in place. It is rebuilding the lists. It's not the most efficient way of doing this. However, it turns out that if your list gets big enough, this quicksort will actually be much faster than any of the sorts that we wrote previously, because it is going to scale for random data as order in log n. Now, because we're picking the first element as the pivot, you can just picture what happens here. If the values are in sorted order, well, then your pivot is the smallest element, in which case before is empty and after is everything but the pivot. And then you keep doing this recursion, and you keep picking elements that are either at the very beginning or the very end. In this implementation, they would always be at the very beginning. And so this degrades to order n squared, and it's not even a good n squared. It would be a really, really slow n squared. But as long as the values are in sorted order, this will wind up being order n log n. And so once n gets big enough, even though it has a fair bit of overhead from building a whole bunch of new lists, it will still wind up being significantly faster than any of the sorts that we wrote previously. So that's it for our quicksort. That's our last look in this chapter at recursion and our last divide and conquer problem. And that's it for now. In the next chapter, we'll come back and we'll look at object orientation.